What we're going to do now is take a look at some examples to really help us build an understanding of how we can categorize or classify real numbers. So as you'll see at the top there, it says to classify each number according to the subsets of the real numbers to which it belongs. So really kind of what that's asking us to do is to say what types of numbers are these real numbers? Are they numbers that are integers? Are they irrational? And we can sometimes put multiple different categories to all these numbers. So kind of the first thing I'd like to do with all of these numbers is if you take a look at all of these numbers, these are all numbers that we could take a number line and we could plot it somewhere on there, right? Like, for example, that 0.38 number, like we're able to plot that somewhere on the real number line. So it turns out that for all 10 of these examples, they're all real numbers, numbers that, as I alluded to earlier, we could use to measure distance or temperature or something, right? So I'm going to say that every single one of these numbers is a real number because they all are. So it turns out that either a number that's real has to be rational or it has to be irrational. You can't have a number that's both of them at the same time. So that's kind of the next thing that you'd kind of want to do is decide, can I identify this number as being rational or can I identify it as being irrational? And how you tell that difference is based on whether or not that number can be expressed as a fraction, ratio, right? Or if it can't be expressed as a fraction. And some key ways to help us understand that is what I described earlier about the decimal versions of these numbers. So in the case of rational numbers, either the decimal has to terminate, what that means is the decimals have to stop, or the decimals are non-terminating, so they have to go on forever, but repeat the same sequence of digits over and over and over as we saw earlier. And then the other case with irrational numbers is that the decimals will always go on forever, it's just they don't repeat the same sequence of digits over and over and over. So that can be really helpful for us to determine if something's rational versus irrational. All right, so let's start with 12. 12 is definitely rational, and the reason why we can prove that is if I write it as 12 over 1, or, I could write it as, 24 over 2, right? We can write that as a fraction. So that's going to be a rational number. 2 and 3/16, pretty clearly, like, that's a fraction. You could write it as 35 over 16 if we converted that to an improper fraction versus the mixed number. So that's also going to be rational because we can write that as a fraction. It is in a fraction form, right? Now, if you look at the next number, we've got 25, and then look at the decimals. That's going to be really important. You can see the dots tell you it goes on forever. So when a number has decimals that go on forever, what we have to look for is we have to look for whether it repeats a sequence of digits or whether it doesn't. And that will tell you exactly if it can be expressed as a fraction or not. So in this case, when it goes on forever, if you look at the decimals, it doesn't look like it repeats the same sequence of digits over and over. It doesn't imply that whatsoever. So because of that, I think we can assume this is going to be pretty random. So let's go with irrational. Okay, because the decimals go on forever and ever, and they aren't going to repeat the same sequence of digits over and over and over. So we can't write that number as a fraction. The next one's kind of interesting. You kind of see that you've got negative 0.574, and you've got the line above there, the 74. So what that really means is it's going to go negative 0.5, 74, 74, 74, 74, 74. So even if there's a decimal or a bunch of decimals at the front that don't repeat, but then at the end of the number, then it starts repeating forever and ever and ever, there is a way that you'll be able to write that as a fraction somehow. So there is that repeating sequence there, so there is a way that you would be able to write this decimal number as a fraction somehow. So it's got that repeating sequence, it's going to be rational. The next number right here is 0.38, and you'll see that the decimal stops. So if the decimal stops, you know it's going to be rational, and we can prove that, and it's really easy to write decimals that stop as a fraction, because if you think this is 3/10 and this is 8/100, it goes out to the hundredth place. So this is 38/100, which means it's 38 out of 100, right? And there's the fraction form of it. Now, of course, you can reduce it to 19/50ths, but that tells you that this number has to be a rational number, therefore. All right, moving over to 0, that's definitely going to be rational. You can write that as a fraction because, I don't know, like 0 over negative 17, right? Like that's going to equal 0. The next number is clearly a fraction because you got a negative 28 and a 4, and that's a fraction, so rational. The next couple examples have square roots. So if you look at the first one, it's got a 32 under it, and then a 9 under the next one. So if you have 32, it turns out that the square root of 32 gives you decimals that go on forever. And we can see some insight into that because like the square root of 25 is 5, right? And then the square root of 36 is 6. So what the square root of 32 is it's 5 point, and then you can type it in a calculator, and then the decimals are going to go on forever and never repeat, right? So it's one of those examples of irrational numbers that I gave earlier on, where we're square rooting something that's not a perfect square right here. So this is going to be something that is irrational. Okay, but the next one, 9 is a perfect square, right? So when we write this is actually just the number negative 3, because the square root of 9 is 3, and then we got the negative in front. And negative 3 is definitely going to be rational because you're able to write that as a fraction. You can put it as negative 3 divided by 1. And the last thing has pi over 2. Now, we know that pi is irrational because it has decimals that go on forever, never repeat, and therefore it can't be written as a fraction. So anytime you, add something to pi or divide it by whatever, it's still going to be the same sort of scenario. So this is going to be irrational. Can't write it as a fraction. All right, so that gives us those categories thus far. Now, the thing about irrational numbers is that we don't usually break that up into any other smaller categories for the most part. So we'll just kind of leave it there if you've got something irrational. But with numbers that are rational, right, we've got smaller categories of integers and whole numbers and natural numbers. And so we'd want to break things up into those smaller categories as such. It's really just identifying numbers that don't have decimals, really, right, and understanding negatives are included in the integers, and wholes start at 0 and naturals start at 1. So let's do so. So with the ones that we identified as being rational, starting with 12, okay, 12 is definitely going to be an integer because integers are counting numbers that are negative, 0, and positive, right? But not only integers, they are also going to be whole because whole start at 0, and not only whole, but also a natural number because natural numbers are only the positive counting numbers, right? So a lot of categories that we can use to categorize 12. Now, with 2 and 3/16, because of the 3/16, right, it's going to have decimals. And integers and wholes and naturals don't have decimals, right? So rational is really going to be the best way that we can categorize that. So I think we're kind of done with that second example. All right, we're going to skip that third example and then go to the fourth example. Again, it's got decimals there. Sorry, I erased some stuff there. So it's not going to be an integer and therefore not be whole or natural. Same thing right there. It's got decimals, so rational is going to be the best categorization there. 0, we can do something about that because we know that 0 is in the integers. And it's also a whole number because whole numbers start at 0. But it's not natural because naturals start at 1, right? The next number is kind of interesting. You've got negative 28/4, right? If you turn that into its decimal form, it's actually just the number negative 7, right? So it's actually just like a negative counting number, which means that this number is definitely an integer, but it can't be whole because whole start at 0 and therefore also can't be natural. We'll skip the irrational one. We know we can't go further with that. And then, this guy, we've basically got the same thing as what we saw just previously because it's just a negative counting number. So we're going to be able to say that that's an integer because negative 3 is that. And then the last example, pi over 2, we know we're done. So in terms of if you were to give a best classification for all of these, right? The most specific classification, that's what I'm highlighting. That's what you would most specifically call these numbers, right? So when you say that this number is an integer, then by it being an integer, it's everything above it, right? You know it has to be rational, it also has to be real. that sort of a thing, right? So I'm just kind of highlighting in yellow there the best classifications that you can give to these numbers. The last thing that I just kind of want to point out here is just at the bottom is just kind of a nice visual that gives you some concrete examples of where we would classify or fit these numbers into the Venn diagram in terms of a best place to put them. So like, for example, if you had the number 0, like you could put it into the rational number category, but that's not the best place to put 0. The best place is where they put 0 in the whole number category, right? You wouldn't put it in the natural number category because 0 is not a natural number. And I just want to make sure that you recognize that there's some kind of fanciful examples that are put into here. So for example, like the square root of 25 is put right there because the square root of 25 is equal to 5. And we know that we can best classify that as a natural number. Or like 4 divided by 2 is 2. You've got some other numbers that have square roots, but it turns out that those numbers 10 and 123, they're not perfect squares. So when you figure out what decimals those numbers have, they're going to go on forever and not be repeating. And there's another example I gave earlier, like with the 2, 5, 255 example, and pi, those are all irrational. So if you just kind of take a look at those examples there, that can kind of help you understand where we can best classify all of these numbers.